Hi, I'm Eva Murphy from Electronic Engineering at IT Sligo, and this is my Leaving Cert Maths Grinds channel. I'll regularly add new videos for both higher and ordinary level maths, so make sure you subscribe below and click the bell icon to be notified of new videos. With the 2011 Leaving Cert higher level calculus question, so this was before Project Maths, however the question's still very relevant, and actually part of it looks like a 2012 question. Part A asked you to differentiate cos squared of x with respect to x. Okay, there's a little trick with any of the trig functions squared. So it's telling you y is equal to cos squared of x. You can write this also as y is equal to cos of x squared. That's actually the same as that. It's just a different way of writing it. But why do I write it like that? Well, to me, it's easier to differentiate it when it's like this, because now I can see it's a chain. So take down the power, reduce the power by 1, and then I must multiply it by the inner function differentiated. So this is a chain. So let's find our trig functions, which are here. Okay, so our cos goes to minus sine. So it's by minus sine of x. Okay, so just to rewrite it, the sine goes first, then the number sine x cos x, or cos x sine x, whichever you want. Okay, so that's the first one. I think much easier when it's written as such. Right, part B, the equation of a curve is y is equal to e to the minus x squared. Find dy dx. Okay, so part B, part 1, dy dx. Okay, so it's an e function. It's e to the minus x squared. So it's chain because isn't that little piece there in itself a function, which means that is a function within the overall e function. Okay, so to differentiate an e function, e to the x becomes e to the x. Okay, so when I'm differentiating something like this, e to a power, that's how I call it, stays as e to the power, but I must multiply it by the inner function differentiated. And I'm just writing that inner function over here for myself. A u is a typical letter that's used in calculus. If I differentiate that, it's take down the power, reduce the power by 1, so it's a minus 2x. Okay, so then in a chain, this is the e function differentiated, and I must multiply it by the inner function differentiated, and we got minus 2x for that. So again, rewriting that, so my sine goes first, my number and my x functions, finishing off with the e functions. So that is dy dx. Part 2, find the coordinates of the turning point of the curve. Okay, so the theory you need to know here is that for turning points, often called TPs, dy dx equals 0. Okay, so this question often follows one where you have found dy dx. So you take your answer to dy dx and you let it equal to 0, and you solve it for x. And that is typically how you find out the x coordinate of your turning point. And then with that x coordinate, I go back to the original function to find my y coordinate. So not back to dy dx, but right back to the original function, because that states y equals. Okay, to solve this for x, you can think of it as it's two factors. So in other words, minus 2x is equal to 0, e to the minus x squared is equal to 0. So a bit like a quadratic where I split it into its factors and I let each of them equal to 0. You discard this one because you can't get logs of negative numbers, which is what I would have to do to solve this for x. So you solve this one. So this is a discard. So you can't get logs of 0 or logs of negative numbers. So minus 2x is equal to 0. X would be equal to 0 when I solve that. Okay, so to find y then, you sub it back into the original. So we're subbing in 0 for x, and we'll get e to the power of 0, and anything to the power of 0 is 1. So that turning point is at x comma y. So that's my turning point. Okay, so the reason I've chosen to do this question is there's little tricks in it. One is writing cos as such, the other is being able to solve something like this for your x coordinate and knowing you discard the other half of it, and the other one is knowing how to deal with powers of 0 or something to the power of 0. So little tricks in this one, but once you know all of that, it is a doable question, but it may take you just a little bit of practice. Okay, that's part 2 done. 3 then says determine whether this turning point is a local max or a local min. Okay, so to determine the nature of the turning point, or of turning points, we only have one in this case, we use d2y dx squared. Okay, which is nothing more than take dy dx and differentiate it again. Okay, so we got dy dx being equal to, if I remember, minus 2x e to the minus x squared. Let me just check that. Minus 2x e to the minus x squared. Okay, so that was my dy dx. So to determine the nature of them, I need to find d2y dx squared. Okay, so now this is a product. There's one function multiplied by another function. Okay, so let's figure out our product rule. So the product rule has 4 little pieces, u and du dx, v and dv dx. Okay, dv dx we know is minus 2x e to the minus x squared from before. Okay, so watch out for this one, especially with e functions. If you're to find d2y dx squared, chances are v is the original function that you started off with. Okay, that can often happen in e questions. So therefore that differentiated then is your dy dx. Okay, you can of course differentiate it again, but I'm just trying to save you a job. Okay, so the product rule then, when we're multiplying 2 product rules by each other, it's u times dv dx plus v times du dx. So dy equals d2y dx squared equals, u comes first, u times dv dx plus v times du dx, okay, which is why I worked out these 4 little pieces over here. So it's kind of a bit like a crisscross. There's u dv dx, v du dx, and then you fill the pieces in. So u times minus 2x dv dx minus 2x e to the minus x squared plus v times du dx. And then let's tidy it up. Minus by minus is a plus. 2 2s are 4x squared e to the minus x squared minus 2 e to the minus x squared. Let's factor out the e to the minus x squared, and we get 4x squared minus 2. Okay, so that's my d2y dx squared. Okay. Right, so to determine the nature of the turning points. Okay, so just to recap, what am I doing? To find the turning points, you let dy dx equal to 0. To find the nature of the turning points, you find d2y dx squared and you test your turning points. So if you remember, our turning point here was 0, 1. Okay, so we're going to test when x is 0, because that is the x coordinate of my turning point. I am testing the nature of this turning point, and it's the x coordinate I use for it. Okay, so to test it, you sub it into d2y dx squared, and you get e to the minus 0 squared, which is 0, 4 times 0 squared, which will all be 0. So that's e to the 0, which is 1. And in the bracket, I have minus 2. So I'm getting minus 2 for that. Okay, now the value doesn't matter, but the sign does. because the theory behind the nature of turning points is as such. So this you have to remember, and I'm going to write it up here in a box. Okay, so d2y dx squared is less than 0 for a max turning point. d2y dx squared is greater than 0 for a min turning point. d2y dx squared is equal to 0 for what's called a point of inflection, or a POI. Okay, so that is the theory you invoke when you need to figure out what is my turning point. So that's what I'm saying by the 2 actually doesn't matter. What I care about is the minus, because that number is a negative number, so it's less than 0. Okay, therefore, my conclusion, 0, 1 is a max turning point. Okay. So I remember it as it's kind of the opposite of what I would expect. This is a minus number, so it's a max. When it's a plus number, it's a min. So I kind of remember that as it's the opposite of what I would naturally expect. If you've enjoyed this video, then why not join us in IT Sligo and use maths in practice. In conjunction with industry, we've designed an exciting new program in electronics and self-driving technologies, which uses cutting-edge techniques such as artificial intelligence, computer vision, and virtual and augmented reality. You'll need a H5 in maths to qualify. Check out the link below.